Welcome to Ask and Learn.
Here in problem 5.75, we have two linearly varying force load densities that span the length of a beam going from point A to point B. Part of the load is downward varying, the other up to span A, and the load density to the right of span A is positively varying. We're tasked with the problem of finding span A such that the reaction force at point B is minimal. And we're given that the load at point A is the value of this load density at point A is 1,800 newtons per meter. The value of the load density at point B is 600 newtons per meter. The total span of the beam is 4 meters. Let's start noting that our total load must be equal to the combined force at each of the end supports at A and B. That's expressed here as total load F sub tot equals F sub A plus F sub B. We also know that since this beam is not rotating in space, torques exerted on this system, the applied torques, must be equal and opposing. We can write these torques as the force of A about the centroid, and that'd be the reaction force at support A, must exactly be canceled by the reaction force at support B about its moment arm, which is for the remaining extent of the beam past the centroid, which is 4 minus x total, the location of the centroid. Using these two equations, we can solve for a relationship of 4 F sub B, the reaction force at support B, in terms of our yet unknowns, total load, and centroid on the beam divided by 4. And that was a couple of algebraic manipulations of collecting like terms or terms that have a common factor F sub B and doing a division. From the previous problem, we derived, and this was 5.74, we derived that the total torque about the centroid of the total load is the polynomial relation 200a squared minus 400a plus 3200. And each of these terms are in Newton meters as their torques. If you'd like to see how that was derived, please see the solution for problem 5.74. We also note that for the reaction force to be a minimum, the derivative of this reaction force as a function of A will have to equal 0 at such a location. And this only guarantees an extreme value. It could be a maximum or a minimum. We would have to verify afterwards, after we find a value such that the derivative of FB in terms of A is equal to 0, if that is in fact a minimum or a maximum. And we can also do that by taking the second derivative of this and noting whether it's convex with a positive value for A or vice versa with a negative value for A, or if it's converse with a positive value. So taking the derivative of our expression, which is this polynomial subbed in for this product up here, I've written that out. The derivative of FB with respect to A is the derivative with respect to A of the polynomial 50a squared minus 100a plus 800, which becomes 100a minus 100. of solving for A in this case gives us a value for A of 1 meter. And again, that's the span for which the reaction force at support B is minimal. Secondly, we're asked to find the values of these reaction forces at each of the ends of the beam. We can do that by using our expression, our composite expression above, inserting in A of 1 meter, as well as, oh yeah, that's all we have to do for this case. And we are left with 750 newtons upward. Solving for the reaction force at support A, we note our first relationship here, F total, which we have already solved for numerically, is the equal to the sum of the reaction forces. So to find F sub A, all we have to do is take our F total and subtract F sub B from both sides. Doing that, and again in our previous problem here, 5.74, we derived that the total load in terms of A is 600 times A plus 1200. We can sub in our numerical value for A now, and we have to subtract our F sub B value, which we just calculated in the previous part. Doing that, our reaction force at F sub A becomes 1,050 newtons upward. And that concludes our problem.